Okay, so chapter 6 or lecture 6 is about monads. So monads are actually quite hard to teach because they're an abstraction. They're something very abstract. So the way I'm going to proceed is to show you concrete examples first. So monads are really an idiom, a functional programming idiom that in essence allows you to get rid of bureaucracy, hide bureaucracy. When we write functional programs, we often have to write quite cumbersome code, and this is what I call bureaucracy here, so you'll see in a moment. So everything will become a bit clearer with the introductory example here. So suppose you have this task to do. You have to implement a function that takes a list of numbers, and it sums up the second, fifth, and seventh items of the list. And if the list is too short, then the function should just return none. So here, of course, this is a quite artificial example, especially, well, the solution that I give here is not the optimal one. You could just check the length up front, and if it's not long enough, then you return none, and otherwise you continue. But even then, you would need this kind of match code, which is basically you try to retrieve the first item, and if it fails, then you fail, you return none. If it succeeds at returning the, second item, so nth is off by 1. It's actually a lie. This is not nth. This is n plus 1 or n plus first. This is what, or no, n minus 1, or regardless. This is zero base. So when you ask for item 1, you're actually getting the second one, which is why we call it n2. And then we ask for the fifth one. If it fails, we fail. If it succeeds, we ask for the third one. If that fails, fail. If that succeeds, then we succeed finally, and we return the sum of the 3 items, which is what was asked of us, right? So that's the solution. And here we start seeing what I mean by bureaucracy, I think, right? So you always have this match with option none goes to none, and then you get the sum. And this code is basically copy-pasted. And you see, every time you do that, you indent by 1 level. So at some point you're going to run into the margins. So it's not a very nice style of programming, right? So the none is basically error handling, and error handling is bureaucracy. You would like it to be hidden. So how do you do that in Java, for example? Well, there you would use exceptions. Right, so list nth would throw an exception, and then you would just continue with the value. You would not have to do this match. You wouldn't have to deal with the exception immediately and throw it again. You could just let it slide through, right? So what we're going to try to achieve now is a functional programming style that resembles exceptions, where we don't have all this bureaucracy. So we'll do one thing at a time. We'll proceed in various steps. We'll refine or improve the above solution. And the first thing we'll do is we'll create a function here called connect, which is going to abstract what is in common with the, you have 3 blocks here that do the same. So connect try to abstract over this code and puts it in one place, right? So that if you have none, then you continue with none. And if you have sum of something, A, then an F is some arbitrary code that continues, then you call this arbitrary code with A. And then we see we can code the function again in a much nicer fashion. Of course, it's more subtle, it's more higher order now. It's harder to understand than the one above in some sense, but at least it's not so redundant. So I called it connect because it takes a bit of program here, which is the beginning, the first lookup, and another piece of code that is the rest of the program. And here we start with a lambda, which is the value that you've extracted from the sum, right? So this sum A, F of A. So the F here is this one here, and it's called, N2 here is set to be A. And then you continue like this. So here's the same thing. You extract the second, well, fifth component of the list. And if that succeeds, then you retrieve it here, and then you continue. And then the same thing here. At the end, you've managed to retrieve all three, right? You have N2, N5, N7 in your hands. And at that point, you can return sum. So you see the idea that the nons have to propagate, and reach the end of the function. And each time you reach a non, you want to stop. This idea is now encapsulated by connect. Okay, so this was the second version as indicated by the subscript here. We can do a bit better. We can use an operation called bind that is part of Lean that is very generic. It just requires a type class has bind. And it turns out that, somebody has already instantiated has bind with option and has done it in the right way. They've done it exactly like we've done with connect. So we don't need connect. We can just use bind. So this is the exact same code, but with bind this time. Okay. Now, for those who like syntactic sugar, we can go further. So instead of writing bind, and then on the left-hand side, what we have is an option. I'm calling my options ma. That might sound strange, but we'll see later this makes sense. So in here, this is a function that operates on the value stored in the option if there is one, right? And instead of writing it as a prefix operator, we can write it as an infix arrow. It's a very strange arrow, but it's standard. It's greater, greater, equal. Yeah, that's what it, that's bind. That's what it looks like. And now this is what the code looks like. Fewer parentheses this time. And yeah, it's a slight improvement, I think, over the previous one. And now comes more syntactic sugar. Yeah, there's no end to it. So we can write do, and then we take the option here, ma, and we can extract the value if it's a sum. And then we continue with t, which is the rest of the program. And this is the same as this bind. So I must say, this is probably going way too fast for you. This is normal. So monads, understanding monads takes some time. You're not going to, spend 1 hour and a half and just like, okay, now I completely get monads. It's a topic that needs to sink in. It's a topic that I myself, understand better and better every year I teach it, which I hope sounds reassuring because this is the third time I teach it now. So don't worry. This is really a lecture where you should not panic, like all the others, of course. But yes, you can. This is all in Hitchhiker's Guide. This is going to come back in the exercises and homeworks, and the exam, of course. So don't worry. Okay, so I was saying there's this new syntax which looks kind of weird with the do, and you can even omit the a and the arrow. But now we're starting to see where this is getting at. So this syntax reminds us of imperative programming. We assign here a value to a variable, and then we assign another value to another variable, and then another value to another variable. And the bureaucracy, again, the exceptions are taken care of in the background. And now we come to the last version, which is that the do's can be combined. So you can just write this. So you write do, and then that enters the whole bind thing. So everything we do from now on is going to automatically bind, right? So we get the first value. If this succeeds, it's get assigned to N2. Otherwise, you just have this option that propagates all the way to the end. Then you have the same thing here, same thing here. Oh, and I forgot to explain one important detail. I'm really sorry about that. So I wrote pure here. Well, pure is the same as option sum. Again, it's a type class, so it has pure. And for options, it's just the same as sum. But here I decided to really adopt bind and pure, not just bind and then sum. That would be an inelegant mixture. So that's why I'm using pure. Pure means, just return that with no error, with no exceptions, right? Which is, basically what option sum does, right? I mean, pure is there because, I mean, if I don't put pure, it's not type correct. We need to have a conversion between, you know, the type alpha or natural numbers and the type option of natural number. And this is where pure comes into play. So I'm sorry about that. And this is where having live students asking live questions would really help. Instead of, I don't know, dead ones. No students at all, I mean. So here, right, so this is the last version, and usually this one is in some sense easy to understand or easy to read. The problem is hard to understand, okay, what does that really correspond to, you know, in terms of bind? So in some sense, it hides the complexity so well that that we don't see it, and then that might, you know, hurt us, because sometimes we actually need to understand under the hood how things actually work. But you see, we've really managed here to hide the complexity of exception handling, and what we're going to and what we've done here is called monads. So this the use like bind and pure together. That's called you know, that's a monad, like in the same sense that you know, groups, for example, right, are an operation like plus, an operation like well, a value like 0, and then an inverse, which is the minus, the unary minus, I believe. So that would be a group, right, and also a type. Well, monads are a bit the same thing. To be a monad, you have to be able to provide pure, and you have to be able to provide bind. And option is a monad. So we were able to use, you know, all the goodies that we get from monads, like the syntactic sugar in particular. That's actually the main goodie of using monads. It's syntactic sugar, and it's a way of thinking, right? So you can do monadic programming without monads. You can just cook them up yourself. There's very little to it. I mean, you saw it. I wrote connect myself, and I was already doing monads without having monads. And this is mostly it. We'll see in the next segment, you know, what a monad exactly is, how they are defined. Oh, and I should add, monads are not just useful for options, of course. That's the whole point. I mean, options is one instance of a monad, but there are many other instances. So, for example, we might want to use monads for if we have a notion of state, and we want to tread through the state, you know, from you know, one line to another, but we don't want to have the bureaucracy of you know, carrying around these variables left and right just because we want to have a kind of mutable state. So monads can provide the illusion of a mutable state. Monads can also be used for exceptions in a grander scale than just having none, right? So we could have you know, arbitrary number of exception states. And so on. We'll see all these instances later, but first, next segment, we're just going to see what is exactly a monad.